Good morning everyone. We are from Vignan Institute of Information Technology from 4th year Chile. I am here to inform you about our project, and our project is about control of DC to DC bidirectional converter for electrical vehicles, and under the guidance of MLS Cyclomaster. And here is our team. This project focuses on the control of a bidirectional DC to DC converter for electric vehicle applications. The converter enables bidirectional power flow between the battery and the PMDC motor, supporting both motoring and regenerative braking motors. A proportional integral derivative, which means PID controller, is implemented for regarding the converter in output and the control of PV motor speed efficiency. The proposed system ensures enhanced energy efficiency and optimizing motor performance for.
So I am here to give you PID controller. So now to regulate the operation of the BDC by PID controller is employed. The PID controller is the converter's duty cycle based on the feedback from the motor speed by continuously evacuating the speed error. This ensures smooth and stable motor operations.
This is the Simlink model of our project. Here we are using a bidirectional DC to DC converter between the battery and the PMDC motor. Here we are using half bridge topology type bidirectional DC to DC converter, which consists of two MOSFETs, MOSFET 1 and MOSFET 2. This is the input capacitor C1, this is the converter inductor, and this is the output capacitor C2, which are helping in the converter operation. Here there are two modes, motoring mode and regenerative mode. In motoring mode, the flow of power is from battery to the motor, and in regenerative mode, the flow of power is from motor to the battery. Here we are using a PID controller for regulating the speed of the PMDC motor. So here we are taking the actual speed of the motor and comparing it with the set reference speed, which is 28 radians per second. The actual speed and the set reference speed are compared, and the error is given to a PID controller block. The PID controller block then generates a control signal which governs the converter's operation. Now we will be having a PWM generator DC to DC, which gives proportionate gate pulses for switching on of the MOSFET 1 and MOSFET 2. Here we are using NOT gate and dead time blocks to split the gate pulses. We are using dead time blocks so as to ensure that the two switches are not turned on at the same time. We are considering the battery parameters, state of charge, current and voltage. Coming to the motor side, we are considering speed in radians per second, armature current and electrical torque. Here P1 and P2 are from and go to blocks, which gives the signal from the PWM generator to the MOSFETs. Now we are giving a torque disturbance to the motor so as to transition between the motoring mode and the regenerative mode. We are setting a step time of 2 seconds and final value of 0.025. Now the system will be acting in motoring mode. When the final value is minus 0.025, the system will be acting in regenerative mode. Now after simulating the model in both motoring and regenerative mode, the results are as follows. The speed increases from 10 radians per second to 28 radians per second, which is the reference speed. The initial peak in the armature current and torque graphs is due to the initial condition of the motor. After reaching the reference value, the armature current and torque reduces to a settling point. And you can also see in motoring mode, the state of charge decreases from 79.761% to 79.759%. The proportionate current and voltage graphs are produced. You have applied a negative torque for regenerative mode. After 2 seconds, the speed increases. Until 2 seconds, the operation is motoring, and after 2 seconds, the operation is regenerative mode. So after 2 seconds, the armature current and torque becomes negative. Occurring in the armature current and torque is due to the transition between motoring and regenerative mode. In regenerative mode, the state of charge of the battery increases. You can see in the graph, the state of charge increases and the current value is negative, ensuring the system is operating in regenerative mode.